Welcome to this homework help video, where we're going to talk about a couple of problems about the physics of waves. So we have two problems. One's a two-parter, and then we just have one question in the second problem. Okay? And they're going to cover two different topics with the overall key idea being waves. Now, in the first one, we're told about a musical frequency coming from a keyboard. And we're told it's middle C, which is just the name given to it. What we care about right here is this numerical value, which is our frequency. So we could write F equals 256 hertz. And hertz are the units of frequency, and there are simply 1/seconds because it's just per time, per second. All right, so this would be something that's happening 256 times per second. And we're told to, with that information, find the period. And to do that, we need the relationship, which is just the definition of frequency and period, how they're related to each other. And that formula is, let's switch over and write this as our key equation. And it is that the frequency is the reciprocal of the period, which is the same as saying that the period is the reciprocal of the frequency, like so. All right, so if you know the frequency, you simply have to just take 1 over that value, and that's going to be your period. So if you have a very high frequency, you have a very short period because, well, each cycle takes less time, has less time it has to be completed in. All right, so it would be a faster oscillating wave. Oscillation is just wiggle, vibration, oscillation. They are all synonyms with each other. So let's go ahead and plug in our value here. And instead of using 256, let's do a higher frequency. We're going to do 7110 hertz. Okay, so much higher frequency, still in the audio range though. And let's go ahead and find this numeric value. So our period is going to be 1 over that 7110, so 7110 hertz. This will be some fraction of a second, which we'll calculate over here. Some calculations left from a previous video. So if you're watching in order, you'll see those and they might look familiar. All right, so let's go ahead and write this in scientific notation. We're dealing with something smaller than a millisecond. So essentially a tenth of a millisecond, which would be a 1/10,000th of a second, okay? And it's 1.4 times 10 to the negative 4. Okay, so that's our numeric value with our chosen frequency there of 7110 hertz. And let's go ahead and write this answer in. So we got our 1.40 times 10 to the negative 4 seconds. Right? Obviously our units are going to be in seconds. All right. And it does actually mention 4 significant figures. It's a lot more than I would think. So you would actually probably want to include a few more, or you might get dinged for rounding in a system. But usually those settings are pretty forgiving, and they probably take it either way. But obviously we could include a 1.406 if we did want to write it with the correct or asked for number of significant figures. So it'd be 1.406 because the 6 would round down or stay at a 6 because the next digit is a 4, which rounds down. And it would still be times 10 to the negative 4. So just look like so. All right. So in part B, we're now going to relate this frequency to the speed of sound in air in order to find a wavelength, which is a really neat step in a problem like this because we've only been talking about an event in the sense of time so far. There's been no movement. But by thinking of this wiggle, this oscillation as a moving oscillation or wiggle, it becomes a wave, and now it's got a defined period, but also a defined length, which we call its wavelength, as it travels out and propagates through the air. Now, the key idea here is that velocity is going to let us actually have an equation to relate these values and thus relate the ideas. So as sound leaves the instrument at a speed of 340 meters per second, this is your often standard speed of sound, which is dependent on temperature. So sometimes you will be given it with different values because of different assumed temperatures, or actually asked to calculate it based on a simple formula that relates the speed of sound in a linear way to the temperature. But all of that is a tangent. What matters here is that this is your often given as your kind of standard 20 degrees Celsius rounded speed of sound at 340 meters per second. Okay, that's called Mach. So if a airplane, for example, a supersonic airplane is traveling twice the speed of sound, they'd be traveling at Mach 2, which would be 680 meters per second. Okay. All right. So now the key equation here, we'll call this our one key equation for the second half of the problem, is just the definition of velocity of a wave velocity. This is wave velocity. You don't always have to put this little subscript name, but here when we're defining it, I think it makes it more clear. And it's simply that the wavelength times the frequency is the velocity. So it's how long your wave is and how fast it's moving is going to be, well, I guess if you took how fast it's moving and divided by its frequency, you would get its wavelength. Or if you think of it as moving in one wavelength worth of distance per that frequency, that's your speed. So it covers one full wavelength in this amount of time, because the wavelength has units of meters and frequency is hertz, which is also 1 over seconds. So we see it becomes meters per second. All right, this would be your velocity. And the wavelength is that shape from beginning to end of the repeating, shape, the characteristic shape of a standard wave. And the mathematical name for the standard wave is the sine wave. And that's just one example of a wave, and there's a whole theory behind waves. So it's all based on this sine wave, which has a length in meters, which is the wavelength. By the way, if you're wondering about the other dimension, it's defined as well, and that's just the amplitude, and it is not addressed in this problem, and it's not a function of the wavelength, nor is the wavelength dependent on the amplitude. Okay, whereas the velocity obviously is. The velocity is directly related to the wavelength. Okay, so let's go ahead then and find that value. Okay, so you can see we have to do an algebraic step to go ahead and solve for the wavelength. And I've been a little remiss here, because when I wrote down this formula, what stands out here is a real oddity, which is this symbol. This is not a normal letter, right? Well, the name of it is lambda, where you would see it in like the keyboard list of lambda. Okay, and maybe without the B, lambda. I'll have to check the spelling on that. But regardless, it's set as lambda. It's a Greek letter, and that's totally the standard that we use for wavelength. Also, we try to stay away from too many Greek letters because they can be a little intimidating, to be honest, right? But sometimes they make a lot of sense. This one is pretty easy to write, pretty distinct. So kind of like pi, it makes sense to use it. And let's go ahead and do the algebra to solve for it. That would involve just dividing both sides by the frequency, because if we went and divided the right hand side of the equation by f, and we did the same on the left side, well, now we would just have lambda by itself. And so we see that we can write the wavelength as just the speed, dropping the subscript wave, we know that's our wave velocity, divided by the frequency, how many times per second it happens. All right, so we're basically essentially eliminating the time, and we're just going to be left with length. Okay, because velocity and frequency both have that time in them. Let's plug in our numbers here, and then we'll plug it into the calculator. So I guess, it's going to be 340 and the frequency we found. And actually, no, we will just use the frequency we're given. We, of course, could use the same relationship between f and t to define the velocity in terms of the period instead. But we already, we're given the frequency outright, or I changed it to this value. So no reason to use our pre-calculated value. Instead, use the one where your significant figures have no question about their accuracy. Okay, so let's just plug in our numbers here. So lambda, and then we're just going to have our velocity, 340 up top. Remember, it's the velocity divided by, zoom out so you can see it, velocity divided by the frequency, all right? And so then we'll just put in that 71110 per second. I'll write it like that, 1 per second, 1 over second. All right, so let's see what number we get. So we're just going to essentially change the numerator in our previous calculation from 1 to 340. There we are. All right, so of course the units have changed, right? But numerically, that's what's going on. We have a length of almost 5 centimeters, right? Almost a 5 centimeter long wave for this particular sound wave. All right, so this being a higher frequency sound wave, it's on the shorter end. A lot of sound waves are longer. Okay, but our hearing range is going to go up almost to 20,000, so they are shorter still. But they become fainter the shorter they get. There is a just due to some properties that there tends to be that effect, which I guess contradicts what I said before. I said the absolute is not dependent on the frequency at all. Well, at least not on a basic level, not taking into account like actual real properties of friction and air resistance and so on. Because it is a mechanical wave that has to move through the air. So okay, so 4.7. All right, 8. And I guess probably sticking with 3 significant figures, so we'd be there because the 7 would round up to an 8, and that would be, we just write it in centimeters, and I'm actually sure the system would accept that, and the online system would. But if you want to write it in meters, you can do it a couple of ways. The scientific notation way, which seems clunky for centimeters because it's so easy just to write centimeter, will be like that. All right. Or of course, you could just leave the leading zeros. So let's go ahead and just write 4.78 centimeters up here for our answer. All right. So that's it for problem 1. Let's wrap this video up by talking about problem 2, which is a beat frequency question. Well, what the heck is a beat frequency? All right, well, it has one key equation that's important for us, and that is just the idea. And it's tied up with the concept. We'll just call it the key equation. That's all we need to know, is that the beat frequency is the difference between the two frequencies that make the beat. So it's just the difference. So the beat frequency, subscript BEAT, to show what I'm talking about here, is just the difference, all right? Now, you can't have a negative frequency, so the difference always has to have the bigger one in front, but how do you do that? You actually write it as the absolute value, which just means that you just make the calculation, you don't care which one is in the front, and whatever you get, you just take the absolute value of it, which means drop the negative if it's negative, do nothing with it if it's positive. And we denote that as a bar, a vertical bar. And so we might as well just put 1, right? Minus 2, or 2 minus 1, it doesn't matter, okay? So that's the beat frequency, the absolute value of the difference between the two frequencies that make the beat, okay? That's what this means, how you interpret it. Well, why is that? That's because there's two separate sounds, like two nearby frequencies, like two slightly different tones, like and I'll try to do something slightly higher. So if those two higher tones were side by side, or happening simultaneously by two different people, then they would create a wobbling sound, which would be because the amplitude is going up and down. It's going from zero to maximum. It's essentially pulsing, and so that essentially dimming or reducing of the sound, and then going back up and going back down, getting louder and softer, and like a pulsing, a couple times per second, is the perception of a wobble of two nearby tones that are discordant. That's a beat, or at least what physics call a beat, not maybe like the same as a beat in music, right? But that's the definition of a beat on a physical level, and it gets related to music theory. That's beyond the scope of the class. Okay, now pretty simple to calculate, just the difference between two frequencies. But we have 3 frequencies, so how's that? Well, that just means we can combine them in different ways. So we can look at the difference between 1 and 3, 2 and 3, right, and 1 and 2. So there's 3 distinct sets, 3 distinct pairings that we can make with these 3 frequencies, right? So let's go ahead and write those pairings out, okay? And this is more the concept of like combinations than any particular math. It's not algebra so much, right? But we wanted to write the, let's see, we just want to have the different frequencies. So I guess I was just going to have, I was going to write pairings, that's right. So pairings. Okay. All right. Well, so 1 with 2. So F. So these all have a B on them. Think beat, right? But they're not. I will actually do this. Is going to be the answer. But our input frequencies, I should label up here. Let's call this one F1, F2, and F3. All right. So no B on those ones because these are the input frequencies. This is the 3 sounds that we're making with tuning forks. If you know what those are, that's a great way to make a pure tone, and you can have them manufactured so they're exactly just a couple of hertz off, thus making a beat that has a frequency of just a couple hertz. Because what I haven't said, and which I guess is an important note, is that this is only like a human perception thing, beats, if it's like, under 100 hertz, and the best of like single digit or low double digits, like 15 hertz, 5 hertz, because that means that it's pulsing in loudness that many times per second. If it pulses in loudness, more than even 30, 60 times per second, we don't notice that. We don't perceive that because that's the kind of the limit of the fastest things that we can, differentiate. In vision, they call it flicker fusion, but maybe here you can think of it as the same thing for ears. Okay, so let's think then. We have our now labeled frequencies. 256, 259, 261, but obviously I'm going to mix those up a little bit. So let's go ahead and go with, how about 252, 242, and 248. Okay, good. All right, so then let's take a look. We're going to have F1 and F2, so there'd be a difference between them. And it could go either way, right? So let's see. So the beat that could get created between them, it wouldn't matter if one was, yeah, it's okay. So if we have two of them, so and we combine the two different frequencies, yeah, there's just going to be the one value of beat. Okay, so then let's say at 2 and 3 then. So we'll pair 2 with 3. Okay, and I guess my point is, if you paired 2 with 1, that's the same as 1 and 2, right? The order doesn't matter. And then finally, we could pair 1 with 3. Okay, so there we go. Those are all the distinct differences. Each of those will make its own beat frequency, which is just the difference between them. All right, so the difference between the frequencies of 1 and 2 is 10 hertz. Right, so because again, we're just sticking with those units of per second or hertz. 2 and 3, that's going to be a difference of 6 hertz. And then finally, 3 and 1, there we're looking at, let's see, 4 by the looks of it. Yeah, 4 hertz. Very cool. So those would be your answers for the, no calculator needed, but it would just be 10, 6, 4, like so. And they actually give you the units. They don't ask you to enter them for once. Okay, so there you go. That's the conclusion of the second problem, all about using the key equation, the beat equation, as the absolute value of the difference between two frequencies, just any input frequency. Here we saw a case where we're combining them in different ways, pairing them up. Okay, so here is all of the homework for this homework assignment about mechanical waves. I hope this homework help video has been helpful. Thank you so much for watching.